Hi, it's Robin. Different setup here for the beginning of the video because I want to use a real CRT to show you a little program I've made. Now this here is a video buddy. It can potentially be classified as a games console, but it has no video output, but it does hook up to a monitor, but in a very different way. I'll show that in a moment. It was released around 1999, and I'm going to make a full video about it. The focus today is on the program I've written, and I'll look at the code just for its own sake that you might find interesting or educational. But just a little bit about the Video Buddy first, which I'll cover more fully in another video. So it's just a battery-operated device. So it has a power switch with a power LED, green and red LEDs to show if you've answered a question correctly, 5 input buttons, and the speaker. And these lights and that speaker are the only output that this device has. You could buy a number of videotapes for it, and they are just standard VHS tapes, but they're specially encoded to enable a sort of a quiz game. They licensed some children's shows and then put their own footage in it along with this quiz that used the Video Buddy. I'll just show a little clip of that now.
Hi there, I'm Video Buddy. I'm so glad you can play with me right now. I bet you're ready to get started. The first thing you need to do is get your Video Buddy handset. Take the suction cup at the end of the cord and stick it right on top of the black dot. Yeah, right there. Next, press the purple power button. Way to go! Now the way this works is that every once in a while during the story, we get to play. I'll ask you questions, and you give me answers. Okay? Every time you hear this sound, you get to answer the question. We're going to have lots of fun, so let's get started.
So the Video Buddy has this cord on it with a sensor with a big suction cup. And the videos all had a black circle in the bottom right corner, which I've recreated on the C64, and then you stick the suction cup sensor to the corner, power up,
Video Buddy.
watch the show, and then at times you'll be asked a question.
By the time all the sand has run through it, I'll be back, okay?
Man, that'll take like forever.
Oh, come on. Remember what we said? Keep busy.
We didn't say it. You did. All right. We'll give it a try. Huh? Come on, everybody.
Hey, it's me, Video Buddy, and it's time to play. Now, every time you hear this sound, press the button with your answer. Sometimes I even ask you to press 2 or 3 buttons for the right answers. So listen carefully. Ready to get started? All right.
And today we're gonna do...
Yippee! Our animal buddies get to paint. What are they going to paint with? Is it toothpaste? Orange juice? Pudding? Milk? Or ice cream? Press the button to choose what they are going to paint with. They are going to paint with thick, gooey pudding paint.
So that's what I've recreated here. The Video Buddy protocol is actually really simple. I thought it was going to be a fun challenge to figure out, but it only took me a couple minutes to figure out once I looked at it. So this program that I've made recreates these top 5 corners of the screen. Each one represents one of the 5 Video Buddy buttons. So if we want to just say that button number 3 is the correct answer, you just put a 1 in that location. You can leave the other ones blank or put a 0 in there. and then press the stop key on the Commodore, and it's actually blinking out the sequence to tell the video buddy what the right answer is. So the correct answer is the third button, the blue one here.
Yes.
And if we just did that same thing, I'll press stop again. It's blinking out. Sorry about the scan lines on the screen. I can't get my camera perfectly in sync with the CRT. Okay, so now the video buddy knows that the correct answer is again 3. I'm going to press button 1.
You can do it.
And it tells you got the incorrect value.
Oops.
And now we'll do the right one this time.
You did it.
Okay, and it also supports multiple correct answers. So we could do 2 and 4. Just waiting 5 seconds while it blinks. You may be able to see the blinking a little bit. So, correct answer 2. It makes that sound if it's a partial answer. I'll press the wrong one.
You can do it.
And this time I'll press the correct 2 and 4.
Great job.
So I was working on a video about Video Buddy, and I want to understand and then recreate the protocol. So I've done that, but I'm making a separate video just to look at the code behind the protocol, because I didn't want to derail that main Video Buddy video with, with a big code walkthrough. But I thought some of you would find the code walkthrough valuable. And yeah, the suction cup sometimes falls off. If you make it wet and gross, it'll often stick a lot longer. And just to show you what the flashing looks like without the sensor in the way, basically it just blinks out 5 flashes. If it's a false answer or like a 0 or whatever you want to call it, then it's a short flash. If it's a 1 or a true answer, then it's a longer flash. And the period between each flash is a full second or 60 frames on NTSC. If there's white for a short period of time, that's a false answer. We'll see the exact values, but it's like a quarter second for false and about 2/3 of a second for true. So again, just press stop and you should see a sequence of short, long, short, long, short to represent this. Short, long, short, long, short. Or if it's just answer 5, it should be 4 shorts and then 1 long. There we go. I'll set my regular capture gear for the code walkthrough. Back to normal. Okay, there's going to be a D64 of these files in the video description. So if you want to download that, like normal, we load up Turbo Macro Pro TMP, 8,1, and then we start it up with sys 32768, and we're in. Back arrow star shows the directory of the files. You might want to check that in case I update the file again with bug fixes or anything. So back arrow L to load VB15, and there's the source. Just to show how to build it before we walk through the code, back arrow 3 to assemble, and back arrow 1 to quit out to basic, and sys 7 times 4096. Or currently we start with sys 7 times 4096. Okay, and that puts the sprite in the corner. By the way, my friend Darren from GrewTube and my Growing Up 80s co-host made that circle sprite for me today on very short notice. So thanks, Darren. And one other thing I didn't mention earlier is that this is interrupt driven mostly out of convenience for me. So I had access to the basic editor. I didn't feel like trying to build a UI, to be able to enter these numbers up in the top corner. So I thought I would just use the basic editor. And then with the interrupt routine, check for the stop button being pressed to trigger the sequence down in the corner. It just really simplified the code side of things to just be able to use the basic editor in this way. So that might be a helpful technique for you for some purpose. Now, by the way, if you want to use BASIC along with a program like this, you need to lower the top of BASIC memory to below your machine language program. Well, I suppose, or above it but anyway, we're going to do below. So I've got 7000 hex because Turbo Macro Pro and the source code are using all the memory above it. So if we just pop into the monitor to calculate this, so our machine language is at 7000, so that's what we want to tell BASIC is the top. The high byte of that is 70 hex, and we can just convert it here. That's 112 decimal. So just remember that. So what all you do is poke 52, 112, and poke 56, 112. And that tells C64 BASIC where the top of string and the top of basic memory are. Both of those. Do a CLR, the pointers to clear memory. And now if we print free, it'll show that BASIC thinks we now have 26 kilobytes free instead of the normal 38K. This is just one example. Of course, you can try to figure out how you want to configure RAM for your particular use. For this is more than enough. Oh, where'd our sprite go? Well, I'll just reinitialize. There it is again. That's funny that the monitor knocked it out. Anyway, that was just an aside. Finally, hit restore, go back into Turbo Macro Pro, and finally, walking through the code. So again, yeah, there's the origin of 7000 hex. I originally tried to put that in the cassette buffer, but my program got too long to fit in there, especially with that sprite, which I also put down the cassette buffer. That's at 828 decimal. So anyway, I just moved it up here. And as is my habit from the C64 Programmer's Reference Guide and User Guide, I set V, the base of the VIC chip, to 53248 decimal, that's D000 hex. Screen memory is at the default 400. These are just labels to use later. We're going to use sprite number 13, which is in the cassette buffer. It's just a nice out-of-the-way place to put a few sprites if you want to use it along with BASIC. A few more labels here, like definitions, defines. Cycle equals 60. So my program does assume it's running on an NTSC machine. I don't think VideoBuddy was ever released in PAL territories, but you'd have to jog these numbers if necessary. Basically, a cycle is how long a flash is, 60 frames, matching the 60 hertz of NTSC video. A wrong answer, that is one of these buttons that isn't a correct answer, should be flashed for 15 out of the total period, while a correct one is 37 cycles out of the 60. And I arrived at those numbers through experiment. Well, actually, I just timed. I had some capture of a VideoBuddy video, and I just captured those flashes and quickly calculated it to about those numbers. The hardware is flexible enough that there's a bit of wiggle room. Probably if your videotape jitters or whatever, it would survive that. Those are the numbers I arrived at. And actually, later I found the patent, and the numbers more or less agree, but the patent's really wordy, and it's not even correct in some places. So anyway. Okay, and there's a total of 5 flashes, one for each button. Okay, the first line of code is jump to init. A lot of the time I'll do this little stub at the beginning of my programs so I know what address to call with the sys command, even if I'm going to use a bit of variable storage near the top right after that. This is just my habit. You can do it another way if you want. And we just need 2 variables, storage locations, the flash count. That's basically like an index that works through as each of the 5 flashes occur. This increments from 0, 1, 2, 3, 4 for the 5 flashes, and I keep it at FF hex when there isn't a flash in progress, so it's kind of like a dual purpose. If the high bit is set, then there's no flash going on, and otherwise there's a flash in progress if the high bit is clear for indexes 0 through 4. We'll look at that later. Frame count is just a counter that goes from 0 to 59. And then once it hits 60, we have some logic to advance to the next flash and then quit. Okay, here's the actual initialization code. This is just that stub I like doing where I set the NMI vector at 318 and 319 to the low and high byte 32768, which is where Turbo Macro Pro lives. And that's a handy way. You can just hit restore and you're back in Turbo Macro Pro. Of course, you should delete that code once you're done development, if you're ever going to do anything serious with your program. Otherwise, if there's no program in memory at 32768, you'll actually get a crash or strange behavior. Okay, next we're going to copy the sprite data that Darren made. Whenever possible, we copy from high to low with 6502 code because it saves one instruction. Each sprite is 63 bytes. So we're going to go from index 62 down to index 0, total of 63 bytes, and copying them from the sprite definition, indexed with X, and then store it at sprite number times 64, X. So it's just doing a copy from our program, copying the sprite into RAM in the correct location. This multiplication is done at assembly time, and it's just a handy way of just using one label to represent the sprite number, that is like 13, but also its position in memory, which is directly tied to it. Every sprite is on a 64-byte boundary, just because that's tidy math, even though the sprite definition is only 63 bytes. So this is just a way of calculating where in memory it goes. And we decrement X, and branch if plus, whenever you want to copy 128 bytes or less, this is a handy way to do it because you can decrement X until it wraps around from 0 to FF hex. Then the high bit will be set and this branch will no longer occur. Okay, next to set the sprite pointer, the first sprite, sprite 0, its sprite pointer is in screen memory at 2040. For this kind of information, the programmer's reference guide is excellent. There's a nice summary here on page 176 titled Easy Sprite Making Chart. So that's just telling the VIC to use sprite pointer 13. We're going to load A with 1, so that turns bit 0 on in these three registers, which are the sprite enable and the sprite expand for X and Y. Yeah, actually for Y and X expansion. Single sprite was too small, so I just expanded it. Even though that makes it more pixely, it doesn't really matter. To position the sprite in that bottom right corner, we set the high bit of this V plus 16. That's the high or 9th bit of the sprite X position. They're all packed into one register. I guess I talked about this in a couple other sprite videos. I'll link to those below so I can just move a little faster through this. So here's the sprite X position, 37 pixels, plus by saying this high bit, that adds 256 to the position. So that moves it over onto the right side of the screen, and a Y position of 212 decimal to set the sprite Y position. 0 is black, and that gets stored in sprite 0's color register, saying the screen and the border to blue. And I did that because I may be using this in another video, and I might use like chroma key, blue screen, to just use that sprite element from the C64 and overlay it on top of other non-C64 video. And this sets the cursor color to 1, which is white. And I initialize that flash counter with FF as discussed previously. That means that there is no flash in progress. Then we hook into the IRQ routine just by disabling interrupts. That means set interrupt disable. A bit confusing. And then we set the low and high bytes of the IRQ routine into these two registers, which normally just point to the kernel routine, which flashes the cursor and reads the keyboard. So we're taking that over. And then we clear the interrupt disable and return. And now our interrupt is enabled. So that's all the setup handled. Now all that's left is our actual IRQ routine, which really isn't all that long. First thing we do is check is a flash in progress. We do that by loading the flash count. And if it's positive, that is if the high bit is clear, then that means that there is a flash in progress. And we're going to go to the process routine, which actually handles the flashing. But if the value in flash count is FF, that means there's no flash in progress. So we're going to check for the stop key. This is a kernel routine that can be called, which I want to point out to any stop key deniers. The actual kernel routine is called stop, and it checks if the stop key is pressed. That's again the programmer's reference guide on page 301. Stop key deniers. Just check the 0 flag. If it's not equal, then we'll exit. But if it is set, then we're going to start a new sequence by just initializing flash count and frame count to 0 to start a new flash sequence. Okay, and either way, we're going to exit by jumping to EA31, which runs the normal kernel handler, which again reads the keyboard, flashes the cursor, etc. So whenever you are doing interrupt code like this, you should always jump there unless you have good reason not to. Okay, and here we'll go into the process routine, which handles the flashing. We're going to load in the X index, the current flash count, which is 0 through 4, actually 0 through 5. We're going to compare X with the flash total, which is 5. If it's less than that, branch carry clear is effectively a branch if less than. So that means we still have flashing to do. We're going to continue. But otherwise, we've reached the end of the flash sequence, and we want to disable flashing, again, just by putting FF in flash count, and then we're going to exit. This could be like a jump. I'm using this as a branch always, because I know after you load X with a fixed value like FF, you know it'll never be 0, so you can use branch if not equal to 0 as a branch always, which the 6502 unfortunately doesn't have. That could just be a jump exit though. Okay, so we still got to do some flashing here. We're going to continue. Note, we're not done all the flashes, so we're going to get the current flash state by loading the Y index with the frame counter for later use. And then we're going to look at the screen memory up in the top left corner where we've put the sequence, and we're going to load it indexed with X to read the screen to find out if we're supposed to be doing a long or a short flash. Now, I could have stored this somewhere else in memory, but because it's just on the screen, I'm just looking it up each time. That just made it a bit easier for me. Now that we're done with using the X, we're going to set the X index to 0, meaning the color black, which is the off state in the flash. And then we're going to compare the accumulator, which has the screen code in it. Is it character code 49, which is the screen code for that number 1 that we put in a slot that we want to have a long flash? If it's not equal to that, then it's a 0. I'm calling it, even though you don't have to literally type a 0 in, you can, but a blank is fine. Any character is fine, besides a 1. So we're going to branch if not equal to 0. So if there is a 1, then we're going to compare the current frame count to right. And up here we had that. Right is 37, wrong is 15. So right is the number of frames that we want a white flash for. So we're comparing Y to right, which is 37. And if it's less than that, then we know we want the flash to be on. So frame counts 0 through 36, the first 37 60ths, we want the flash to be on, that is white. and I let it fall through here, or we branch here from the 0, we're going to compare Y with wrong, which is the 15. So if it's a 0 and the frame count is less than 15, then again, we want the flash to be on. Whether it's true or false, there's a flash, but it's a shorter flash if it's a wrong answer. I could have had here a branch of carry set to finish, but I chose to just let it fall through because if it's greater than or equal to right, that will also absolutely be greater than or equal to wrong because that's a smaller number. So I saved an instruction, but it does cause it to execute a few more commands. Anyway, it's just a random optimization. Obviously, this isn't fully optimized, but that's an idea for you to consider for optimizing. You can let other code run that you know is safe. We call that falling through sometimes. Otherwise, we're going to jump to finish. If we do want to flash, that is, if we've branched to on, either because the frame count was less than right or less than wrong, then we're just going to increment X. So it'll go from 0, which is black, to 1, which is white. And then either way, we end up here at that finish label, which stores X, 0 or 1, black or white, into the sprite color. And then just a bit of cleanup. We're going to increment the frame counter, which is going from 0 to 59, and we're going to check, has it reached 60? If it hasn't, we're going to branch to exit because we're done. But if it has reached 60, then one more flash cycle is complete, and we're going to reset the frame counter to 0 and increment flash count from 0 to 1, from 1 to 2, all the way up. When it reaches 5, then that code above will catch that and end the flash. So let's increment it. This is, again, a branch always. We know that after incrementing flash count from 0, 1, 2, 3, 4, 5, that the 0 flag is never going to be set. We're never going to increment flash count from FF to 0, which will make this true. So this is essentially another branch always. And that's it for the code, and all that's left is that sprite data that I got from Darren. That's 63 bytes worth. That's a look at the VideoBuddy Flash code. I acknowledge that maybe nobody's ever going to use this code as is. It's like, who has a VideoBuddy in the first place, and who would want to hook it up to their C64? Probably nobody, but I hope some of the techniques here discussed you might find useful in your own programs, or it just might be interesting, educational. So depending on when you see this video, you might see it before I have created the actual VideoBuddy episode. If you're one of my patrons who sees the exclusive videos, then that VideoBuddy episode will be coming sometime later. If you're not one of my patrons, why not? The VideoBuddy episode will have already been released, and then this is kind of a follow-up, a look at the code behind the flashing corner. Okay, thanks very much to my patrons. Thanks for watching, and we'll talk to you next time.